So this is an applied optimization problem. So we have to design a cylindrical can of volume 900 cubic centimeters, so that we use least amount of metal. That's simply to minimize the surface area of the can, including its top and bottom. And then the second part of the question is to determine whether it is possible to design a cylinder of the same volume with the largest possible surface area. So let's demonstrate how to solve this problem. Now, we need to say draw a sketch of a cylindrical can and fix some dimensions of the can, and then use the known formulas from calculus to be able to interpret the problem perfectly. So let R be the radius. Let H be the height. And let A be the surface area. And let's have V, capital V, be the volume. This is what we have. So if we have to draw, we have this. So roughly this is the diagram of the can. So we have a radius of R units, height of H units, or centimeters now because already volume is given in centimeter cubed. So we know from our high school mathematics that surface area of this cylindrical can is given by pi r squared, which is the say top surface, and then plus pi r squared, which is the area of the base, and then plus 2 pi r h. This is the curved surface area. So which, when you add all this, we have area is 2 pi r squared plus 2 pi RH. So this is a starting point. You don't remember the formula for finding the surface area of a closed cylinder, then you'll not be able to proceed. And also, volume is given by pi r squared h. Now, since we have been told that the volume should be 900 cubic centimeters, then this implies 900 is the same as pi r squared h, which means h itself will be given by 900 divided by pi r squared. So let's call this one formula 1. Let's call this one formula 2. So we can now say replacing 2 in 1. This simply means now where there's h we replace by 900 over pi r squared, we get area will be given by 2 pi r squared plus 2 pi r, but where there's h we put 900 over pi r squared. So in simplifying, we get area now, which will be simply a function of r, will be given by 2 pi r squared plus, so 1 r and r cancels, so we'll have 2 by 900 is pi, and pi also cancels out. So we'll have 1800 divided by r. So let's call this one formula 3. So we have successfully expressed our area as a function of radius, or we have simply expressed a in terms of r, because pi is just a constant. So with this area formula, then you know that always radius is a distance or a length, and length are always positive. So we can say the radius is very key, that we are going to do our operations or minimization process on this interval 0 to infinity, because radius can only be a positive value. So with this formula 3, there are key things that we can note on this one. So note from formula 3, the area is having 2 terms, and then these 2 terms display 2 characteristics of this area function. That one, area tends to infinity as r tends to infinity. Now this is because of the first so you see, when you make a radius to be a very large number, then this first term will also blow up, or will also be a very large quantity, because we are squaring the value of r. So then area becomes also a very large quantity. So that's why I'm saying that area approaches or tends to infinity as r tends to infinity, because of this first term in the expression of area. Number 2, area also approaches infinity as r approaches 0, because of the second term. So this can easily be seen here. So taking this one fixed here, then interpreting this part here, when you make r to be a very large positive value, because 1800 is fixed, then you are making the denominator to be a very large value. So this thing will actually tend to, this part will tend to 0, and then this part will also be making the value of the area to be a very, very large positive value. So therefore, with this area must take So because of these two ideas on the area function, then we know that the area can only take a minimum value at the critical point in the domain of the function A. And so we solve in the usual way. To get the critical points, we need to get the first derivative and then equate to 0 and solve the value of R. So we solve the A, the R equals to 0 to obtain the critical points. IA. So since we have our area function as A given by 2 pi R squared plus 1800 over R, then this means the ADR be given by 4 pi R minus 1800 over R squared. Remember, this term can be written as 1800 R raised to power negative 1. So that explains why I have this as a minus sign. And then we equate this one to 0. So this is the same thing as writing 4 pi R equals to 1800 over R squared. And then to get the value of R, we cross multiply both sides by R squared. So which means 4 pi R cubed equals to 1800, which means R cubed alone will be 1800 over 4 pi. And then to get R alone, we get the cube root on both sides. So defining the cube root of this right-hand side, we'll get R to be 5.23223868 centimeters. Centimeters because the volume was given us in centimeter cube. So that is the value of R. And then H, we have seen that H is given by 900 divided by pi R squared. So which will be 900 divided by pi 5.23223868 and then squared. When you work out this, I will get that H will be given by 10.46447736 centimeters. So therefore, we can say to design a cylindrical of volume 900 cubic centimeters, so as to use less or actually least amount of metal we need to have a cylinder of radius 5.2322 and or with the height of 10.4645 centimeters. So this is the solution to the first part. And then part 2, the question was, is it possible to design a cylinder of volume 900 cubic centimeters with the largest possible surface area? So now, from one above, we have that the area function is given by 2 pi r squared plus 1800 over r. So this is the function describing the surface area of this given object. Now, so this function has no maximum, because it tends to infinity. As the value of r approaches 0 or r approaches infinity. So this can be seen if we draw the graph of surface area against radius, we'll get this structure. If this we plot surface area and we plot radius, then we get a graph of this form. So something here is around 5.2322. So this is the function A given by 2 pi r squared plus 1800 over r. So because of this, we don't have bounds, we don't have an upper bound for this value of the function A. Hence, we say, therefore, it is not possible to have such a case. So this means that a cylinder of radius or a cylinder of such volume So I was saying that a case of having a cylindrical can of volume 900 cubic centimeters to have a maximum surface area is not possible. And then the only scenarios is that a cylinder of fixed volume has a large surface area if it is either very fat or very fat and short. This means R is very large, or very tall and skinny when R is small. So this can be shown from this. So we can either have these scenarios or we can have these scenarios. So note that from the answers we obtained in the first case, we got R was 5.2322, and then H is 10.4645 or simply 44. So these two measurements from our calculation obey or have a relationship that H is the same as 2R. So the optimal dimensions from the first case shows that whenever you want to have to use less material, then you need to ensure that the radius height is twice the radius as per the calculation in the first problem. So the real thing or the main concept that was being tested on part 2 was to know whether you can interpret this area function to see whether it has a maximum or a minimum value. And then from the interpretation of the limit, as R grows larger, this function, you see that there's no maximum. So if there's no maximum, then it is not possible to design a cylindrical can of volume 900 cubic centimeters to have a possible largest surface area. That's how we're supposed to solve that problem. Question 1C. Thank you.